Hello there, Mr. Sutton here, bringing you the AB Calculus 2-6 Extra Practice Number 1 solutions on continuity. For this problem, we're given this function f here, this big polynomial, and we want to know for how many positive values of b does the limit as x approaches b equal to. Alright, so the key on this one, since this is a polynomial, we know that this is a continuous function, which means that the function value and the limit are going to match up everywhere on this function. So when I'm asking for how many values of b does the limit equal to, I'm basically asking for how many x values on this function does the output equal to. So basically I have to figure out where does f of b or f of x in general have a value of 2. And to do that, I have to graph this thing out and see how many times it intersects the line y equals 2. Now, another key on this is they ask how many positive values of b, so how many positive x values. So I'm only going to consider things to the right of the y-axis. So let me go ahead and put this in my y equals on my calculator. So here I am on my graphing calculator. I've entered the original function as y1. I've entered 2 as y2 because I want to know where these two things intersect. And I'm not really sure what window I should have. Let me just make a window that goes from 0 to 10, and we'll see what we get. And then let me just do, let's see here, let's just graph it. Okay, so there's my polynomial. And here's the line y equals 2. Now we see that there's clearly at least one place where we're crossing. This other place we're not too sure about. So this is the general picture here, and I have the rest of it included before the y-axis in this picture, but we know this doesn't count over here. So we're at least in for one. We might have as many as 3, depending on how many times we're hitting in this spot here. One thing we do know for certain, though, is that we can't have more than 4. The solution to this polynomial equaling 2, since it's fourth power, we have at most 4 solutions to this. So if we've got the one here for sure, this one doesn't count, but it counts as a solution in general. If we have another 2 here, then we know for sure that we've got all the solutions that we could possibly ask for on this. So let's zoom in a little closer on that spot of the graph. So let me do zoom, and let me do my box here. And then let me move a little bit closer. So there's my spider. There we go. Let's move a little bit closer to that intersection. And let's just open a box so we can zoom in as far as we need to. So there's the polynomial again. And here's the line going through it. It looks like it's hitting it in just one spot, but it's really hard to tell. So I'm going to zoom in a couple more times just to really be on the safe side. So let me do zoom box again, and we're intersecting somewhere in this area. Let's just be really sure that we're only touching that once, because it's kind of hard to tell. All right, so there's our function again. And oh, look at that. It looks like we are touching twice. Well, I'm glad I zoomed in a little bit more. So there was the situation. So overall, we have 1, 2, 3, 4 intersections, but only 3 of them count because only 3 of them involve positive x values. So this is 3 positive values for b, which is what they're calling the x values here. That means that we've got answer choice C after all that. On this one, we have a table with selected values for a continuous function f. That means we're not jumping all over the place. We have a smooth progression from one point to another. Based on the data in the table, we want to know the best approximation for the limit at x equals 3 for f of x. So just taking a look at the table, as we approach the x value 3 from the left side, our limit appears to be heading towards 5. I mean, it's kind of hard to tell exactly what it should be because, I mean, tables, you're always missing information, but they asked for an approximation, so we're guessing the limit from the left is 5. And then taking a look at the limit from the right side, as we approach 3 from the right side here, our numbers are going up, 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 and it looks like we're also heading towards 5 from the right side. Therefore, our approximation for our two-sided limit is going to be 5. Now, there's some other answer choices here to look at. I mean, 5 is one of the answer choices, and that's the one we're going to pick. But in case you were wondering about the other ones, so 0 and 3, I mean, You could argue about 5 just because you don't know everything about a table, but 0 and 3, there's definitely no way to pick those instead of 5. Really, the only plausible alternative is choice D. There's no best approximation because the limit does not exist. However, we know the limit exists. How do we know the limit exists? Because they said this was a continuous function. One of the conditions for continuity is that your limit exists wherever you're continuous. So therefore, choice C is the only thing we can pick here. On this problem, I've got this f function defined by this piecewise function. Based off of this, we want to know which of these statements is true. All of these statements are dealing with the behavior of our graph at x equals 2. And of course, 2 is the border value of this piecewise function. But it's kind of an interesting piecewise function. This isn't one of those where you have one rule for less than 2 and one for greater than 2. This one, we have a single rule for all the values of x that are not 2. And then another rule for exactly 2. So this 7 rule isn't doing a whole lot, but it's going to be important in this problem. So to figure out whether we are continuous or have some kind of discontinuity, we're just going to go ahead and start proving continuity and see what happens. One condition of continuity is that your limit has to exist. Specifically, in this case, our limit at x equals 2. So let's try to find the limit at x equals 2. To do that, which rule do we have to use? Well, we always have to use rules that involve the x values that are close to the value we're trying to find the limit at. So we don't want to use the rule for exactly x equals 2. We want to use the rule that involves, for example, 1.999 and 2.001. Both of those values are going to fall in this x does not equal 2 rule. So basically, we have to plug 2 into this x not equal to 2 rule right here. That's a problem, because this x minus 2 down here, that's no good. That's giving us a 0. And if we plug 2 into the numerator, well, this would be, let's see, 8 minus 6 minus 2. That's also 0. So we have to do a little bit of simplifying in order to plug 2 into this top rule. So we're going to have to factor it. What does this factor into? Well, since we're getting 0 over 0, that means that there is a hidden x minus 2 factor in the numerator here, along with this x minus 2 in the denominator. Otherwise, you wouldn't be getting 0 over 0 by plugging in 2. So I know I can factor this into x minus 2 times something in the numerator. Times what? Well, to get 2x squared, I'd have to multiply this x by another 2x. And to get negative 2 as the constant, this negative 2 needs to get multiplied by a positive 1. So my other factor would have to be 2x plus 1. But just to double check, x times 1 would give us 1x, negative 2 times 2x is negative 4x, both of which combine to give us the negative 3x in the middle if we were to multiply this out and simplify it. All right, so this is good news. We can cancel out these x minus 2's that were giving us trouble. So really, I'm just finding the limit as x approaches 2 of 2x plus 1. So now I can just plug 2 in for x. That's going to be 2 times 2 plus 1, 4 plus 1, which gives us 5. So a couple things come out of this. First off, the limit is 5. This is heading towards 5. Second, the limit exists because it's a constant. So that allows us to eliminate choice C, which has a jump discontinuity. Limit does not exist at a jump. You're going to different places as you approach the same x value. We also can't have a vertical asymptote if the limit exists, because if we had a vertical asymptote, this limit would be some kind of infinity. But it's not. It's a constant, can't have a vertical asymptote there. So now let's just keep going with our continuity proof. The other piece of continuity, one other piece, is that your function has to exist at the x value. Well, what is f of 2? F of 2 is going to use this rule where x equals exactly 2, so it's just going to return the constant value 7. So that exists. We've met the first two conditions of continuity. But the last condition is that the limit at 2 and the function value at 2 have to be the same number. And clearly, they are not. Because the limit and the function value do not match up, that means that we do not have continuity. So that eliminates choice A, and all that's left is choice B. And this makes sense that this would be a removable discontinuity because you have a function that's heading towards the same place from both sides, but when you actually get to that spot, you have this little dot at 7 that doesn't line up with the rest of the graph. So that's definitely a removable, giving us choice B. For this problem, we're told that a function f has a jump discontinuity at 3. So which could be the graph of f? You basically have to know what a jump looks like. So choice A, that's a removable. choice B isn't any kind of discontinuity. That's a cusp, which we haven't really learned about yet if this is the first time you're seeing continuity. But it's continuous. That's the important point for this question. C, this is a jump. Our limits are different from the left and the right, and they're finite limits, so it's a jump. And then choice D, this is an infinite discontinuity, an asymptote, so it's not a jump. So then that means choice C is the one we want. On this question, we're told that the graph of f is shown in this figure, and we want to know where f has a removable discontinuity. So removable discontinuity is just a fancy name for a hole in the graph. So looking at our options here, let's see, at x equals 1, this is a jump, so that's not exactly a hole. Choice B, x equals 3, that is a hole, so that definitely works. I'm just quickly looking at the other answer choices. 4, right here, that's not a hole, that's a continuous spot. And 5 looks to be an asymptote, so then choice B, x equals 3, is what we need here. For this question, we're told that the limit as x approaches 6 of f exists and is less than 5. We're also told that f of 6, the function value itself at 6, is 10. Which of these statements has to be false? So going through each of these here, we've got the left side limit is 0, right side limit's less than 5, left and right side limit equal each other, and then our other option is that f is continuous at x equals 6. Well, if the limit exists at 6, that means that the left and the right limit have to match. So that already eliminates choice C. This has to be true if our limit exists. So, and we're looking for the statement that's false on this one. Now, we also know that the limit is going to be less than 5. Well, if the limit's less than 5, that means the left side limit has to be less than 5. So the limit equaling 0 could certainly be true with that condition. And also, that's basically what we're saying in choice B, is that our limit is less than 5 as we come from the right side. So each of these is going to be some number less than 5, which means that A and B could both be true, so neither of them has to be false. So we can already eliminate choices A and B. So really all that's left is choice D. Now, to really just kind of drive the point home and see why this has to be the only false statement here, let's look at the other piece of information they gave us. They told us the function value at 6 was 10. Well, if the limit has to be a number less than 5, and the function value itself is 10, 10 is greater than 5. So there's no way that the limit and the function value at 6 equal each other, which means that our limit and our function value cannot equal each other. If these two things don't match up, then we've proven that our function is not continuous at x equals 6. So that would have to be choice D. This is the only thing that has to be false. On this problem, we're given this piecewise function, and we want to know which statement is true. So these are all talking about the behavior of the graph at the border value x equals 1. One option is that we're continuous at x equals 1, and the other three options are we are not continuous with various reasons given. So let's go through and try to prove continuity and see what happens. So for continuity, the left and right limits have to equal each other because the overall limit has to exist, and the function value has to exist and equal the overall limit. So let's take a look at our left side limit. So as we approach 1 from the left side, we're using this rule where we have x values less than 1. So that's 2 to the 1 power, which is just 2. As we approach 1 from the right side, now we have to use this rule for values greater than 1. So that's going to be, let's see, 1/2 minus 1 is negative 1/2, plus 5 halves is positive 4 halves. That's going to equal 2 as well. So our limits match up. That tells us that the limit at x equals 1 does exist. So if this thing is not continuous, we can't say it's because the limit doesn't exist. Choice D is not going to be option regardless of what happens with the rest of our analysis. But we have to keep going. The limit existing is not enough. We also have to have a function that exists, and it has to also equal the limit. So if we plug in the value 1 itself into this function, what happens? Well, there has to be a rule for x equals 1 for us to get anything out of this. And if we look at this function, we have rules for x less than 1. Here's a rule for x greater than 1. We do not have a rule for x equals 1 exactly. So that means that f of 1 does not exist for this function. And if your function value doesn't exist, that already blows continuity out of the water. So we would say then that we're not continuous because f of 1 does not exist. So that would be choice B. For this problem, we're trying to figure out which of these functions is continuous at x equals 3. So let's just go through each of these and check limits, function values, and see if those things match. So to find the limit at x equals 3 for the f function in choice A, we need to use this first rule here, because I'm seeing what's happening as we approach 3, but that means we're in the not exactly equal to 3 jurisdiction here. So taking the limit of this rational function, I'm going to actually factor this and cancel before I plug 3 in, because if I plug 3 in right away, I'm just going to get 0 in the denominator, and probably the numerator too. So if I factor the numerator, things that multiply to negative 12 and add up to 1, that would be x minus 3 and x plus 4. Canceling out the x minus 3's, we've got limit as x approaches 3 of x plus 4. And then plugging in 3 there, this is really just going to come out to 7. Okay, let's see the function value now if we plug in 3. F of 3 itself does exist. It's 8 based off of this x equals 3 rule. The trouble, though, is that it does not match our limit at 3. Because these two things don't match, that means that we do not have continuity at x equals 3. All right, well, on to the next one then. Choice B, analyzing the g function. So we could test out limits, certainly, but before we do that, take a look at this. At x equals 3, we are undefined. Since g of 3 doesn't even exist, we're pretty much done. We don't even have to check the limits. We know this is not going to be continuous at x equals 3. Moving on to the next one. Let's see. We're defined at least at x equals 3. Let's check the left versus the right limit. For the left limit, we're plugging 3 into this less than 3 rule here. So if we do the left side limit, that's going to be, let's see, sine of 3 pi over 2. That's going to be negative 1 times negative 8 gives us positive 8. And now the right side limit as x approaches 3, that's using this rule down here. So now we have cosine of 3 pi, which is the same as cosine of 1 pi, which is negative 1, times negative 8 gives us 8 again. Yay, unit circle trig. So those match up, meaning that our limit does exist. The function value itself is 8. So since our limit exists and matches the function value, which is what this statement here is capturing, that means that we are continuous at x equals 3 for the h function. So it looks like choice C is what we're looking for, but let's just take a quick look at choice D to be on the safe side. So the left side limit for the k function here, if you plug in 3 to this less than 3 rule, this is the ln of 1, which is 0, so that comes out to 8. And if we do right-sided limit, we're going to be doing 8 times the ln of 1, basically. That's 8 times 0, which is 0. Well, the limits don't match up, so that means the limit does not exist for the k function, which rules this out for continuity. So we've confirmed it. It's choice C. For this problem, we're given this f function, which is this crazy-looking rational function with a's and b's in it, where a and b are constants, and they're saying the graph of f has a horizontal asymptote at y equals 3 and a removable discontinuity at x equals 2. So given this stem here, the first thing we're asked to do on this problem is show that the a value is 6 and the b value is negative 13. So the fastest way to do this is to actually plug these numbers into the function and see if we can get these results with the horizontal asymptote and the removable discontinuity. So rewriting this with a and b, we can write this as 6x squared minus 13x plus 2 all over 2x squared minus 8. And now to test out each of these, let's do the horizontal asymptote first. That one's fairly easy. Horizontal asymptote at 3, you're basically saying as the limit as x approaches infinity of this function needs to be 3. So let's check that out. Limit as x approaches infinity, or negative infinity. Since it's a rational function, they'll both give you the same asymptote. So now, doing a little choose your champion reasoning here, we're just going to use the principle of dominance and forget about slower growing terms. So in the numerator, all we really need to consider is the highest term here, the 6x squared. In the denominator, it's the 2x squared we're looking at. And now we can see we can just reduce these to give us an answer of 3. So this shows that we do have a horizontal asymptote at 3 if we have this a and b value. Okay, so let's move on now to the next piece of this, because we still haven't shown that we have a removable discontinuity at x equals 2. To demonstrate that, we basically need to show that when I plug in 2 for x using this a and b value, I get 0 in both the numerator and the denominator. If I've got that indeterminate form, that proves that I have a removable discontinuity. Okay, so let's go ahead and do that. Plugging 2 in, we've got 6 times 2 squared minus 13 times 2 plus 2. So this is going to be, let's see, 6 times 4 is 24, minus 26 is negative 2, plus 2 is 0. So that checks out for the numerator. In the denominator, we've got 2 times 2 squared minus 8. So that's going to be 8 minus 8, which is also 0. So since we end up with 0 in both the numerator and denominator, note that I didn't write 0 divided by 0 because that's just mathematically bad. But I wrote them separately. This shows that we have a removable discontinuity at 2. On this next part of the problem, to make f continuous at x equals 2, which it isn't because they said we had a removable discontinuity there, but to make it continuous, f of 2 should be defined as what value? So they're basically saying they want to set up some kind of piecewise function where this is the rule for x not equal to 2, and for x equal to 2, we're just going to define whatever value this wants to equal. So how do we figure this out? Well, let's just first establish what this looks like again. If a is 6 and b is negative 13, then again we have the function 6x squared minus 13x plus 2 over 2x squared minus 8. So that's our starting point. And notice that I factored out this 2 just to get the ball rolling here. So this is really x squared minus 4 inside. That'll be a little bit helpful later on. So now in order to figure out the value that f of 2 should be, we want f of 2 to equal the limit of this function here. We know that if we plug in 2 right away, we're going to get 0 over 0. We demonstrated that in part A, and that's no good. But a removable discontinuity, the nice thing about it is that you can remove it, usually by factoring and canceling. So we're going to go ahead and do that and find the limit as x approaches 2 of f of x, and that's the value that we're going to make sure f of 2 equals in whatever piecewise function they want to set up. All right, so to take this limit, we already know we get 0 over 0 if we plug in 2 right away. So let's do a little factoring. Now the numerator looks kind of nasty to factor, but one thing that's going to help me out here is I know already that one of the factors must be x minus 2. I know this because when I plug 2 in to this expression, I get 0. That implies that x minus 2 is one of the factors. So I have x minus 2, and now I just have to figure out what I have to multiply by x minus 2 to get the rest of this. So to get 6x squared, I need to multiply x by 6x. To get positive 2, I need to multiply negative 2 times negative 1. So then we have 6x minus 1, and if you want to double check, x times negative 1 is negative x, negative 2 times 6x is negative 12x, adds up to negative 13x, so we're good. And now the denominator, we have to factor that as well. This will be x plus 2, x minus 2. Still have that 2 hanging around. And at this point, we can cancel out these x minus 2's. That removes the removable discontinuity. And at this point, we are free to plug 2 in to see what this limit will actually evaluate to. So we're going to have 6 times 2 minus 1, 2 times 2 plus 2. This is 12 minus 1, which is 11, over, this is 2 times 4, so 8. So we want f of 2 then at the beginning of this string of reasoning. We said we wanted f of 2 to equal this term here, positive 11 over 8. For this problem, we want to know at what value of x does f have a discontinuity due to a vertical asymptote. We already saw we have a removable at 2, but how about a vertical asymptote? So for this, we're going to have to go back to part B. In part B, remember, we simplified our function to be 6x minus 1 over 2 parentheses x plus 2. And I'm going to rewrite this here, and I'm going to call this f of x with the condition that x does not equal 2. So that accounts for that removable discontinuity that we just canceled out, but by writing x not equal to 2, I can treat this as the original function. Okay, so now once I've got this simplified version of the function, I just need to figure out what zeroes out the denominator at this point. So we're going to have a vertical asymptote wherever 2 parentheses x plus 2 equals 0. That happens at x equals negative 2. And if you wanted to double check, you could say if I plug negative 2 into the numerator, I don't get 0. Therefore, I have a vertical asymptote. That was another way to do this. But by showing the simplified function and where we got this from, we've met the burden of proof.